Am I audible? Okay. Good morning, everyone. I am going to talk on search for supersymmetry in events with a lepton, photon, and missing transverse momentum final state using full Ron to CMS data. So we know that standard model is successful in describing the structure of matter and interaction between them, but still it has many shortcomings. And supersymmetry is one of the most motivated BSM theory, which describes many of the shortcomings such as hierarchy problem, unification of gas coupling, and it provides candidate for dark matter. So theory of supersymmetry proposes that for every standard model particle we have a SUSY partner. So we have S quark, S lepton, gluino, and as the super partner for gas boson we have neutralino, chargino, and gluino. And we consider R parity conserving SUSY model, where R parity is defined as minus 1 power 3 times baryon number plus lepton number plus 2 times spin. The standard model particles have R parity plus 1 and the SUSY partners have R parity minus 1. For example, two SUSY topologies are shown here. PP collision produces a pair of gluino which further decays to standard model quark and neutralino. Similarly, a pair of S quark is produced from the PP collision and it further decays to standard model quark and neutralino. So we have multijet and mat in the final state. I will discuss on the SUSY signal we target for our analysis. We look for gas mediated SUSY breaking scenario where gravitino is the lightest supersymmetric particle. So it is the super partner of hypothesized particle, that is graviton. It has spin 3/2 and this is taken to be the massless LSP, and for us neutralino and charginos are NLSP having equal masses. So we look for pair production of neutralino and chargino from PP collision, and it further decays to W boson and photon, and W decays leptonically. So in the final state we have a photon, lepton, and missing energy from neutrino and gravitino. So this is the electroweak production channel, that is T5WZ. The other process we target are strong production process. Those are T5WZ and T6WZ, where from proton-proton collision we have a pair production of gluino and pair production of S quark, and which further decays to neutralino and chargino pair production, and the similar decay chain continues. So in the final state we have in the strong production cases we have number of jets, and electroweak case we have photon and lepton and mat. So the major standard model background for this signal topologies are W or G plus photon, when we have leptonic decay of W or G, and we can have a fake object, that is we can have a fake lepton or fake photon, and that can mimic this signal. And we can have also other electroweak process such as TT gamma, WW gamma, or WG gamma. I will be discussing all this background estimation in detail. So for this analysis we use 138 inverse femtoven data collected by CMS detector from 2016 to 18. To select out electron photon events we use the diphoton trigger. For selecting mu1 photon events we use mu1 photon cross trigger. We require an event to have exactly one photon and at least one lepton, and the PT threshold of lepton is more than 25 GeV, and for photon we require it to have PT more than 35 GeV. The photon and lepton are required to be separated by a radius of 0.8 in the eta 5 phase space. To have a minimal contribution from the Drellian events, we put some selection on the invariant mass cut, that is the mass difference between E gamma and mass of G boson should be more than 10 GeV. For this analysis the variables used are photon PT, mat, ST, and transverse mass of lepton and mat system. Mat is defined as magnitude of negative vector sum of PT of all particles in the event, and it is the missing energy of the event. And similarly ST is the hadronic activities in the event, that is the scalar sum of PT of all jet. We carefully define the control region which has similar kinematic properties as that of the signal region, but it is dominated by background. And we establish all our background estimation methods like calculating fake rates and scale factor in the control region, and then we move to the validation region where we check the where we validate our background estimation methods, that whether the data agrees with the all total standard model background. And once this is done, we move to the signal region where we expect a significant number of SUSY signal events to be present, and these are the regions defined as mentioned here. So further, the signal region is binned in terms of variables like MET, ST and photon PT. So we have a total 36 search bins, 18 bins for E gamma channel and 18 bins for mu gamma channel. So moving further, here are three categories of background. First one is fake object. We can have a fake photon or a fake lepton, and we have a true background, that is W or G plus gamma. It has definitely have a lepton and photon in the final state. And the third category is TT gamma, WW gamma and WG gamma, which have a less contribution to the data. So this all fake backgrounds are estimated using data driven method. One point is to mention here is that fake lepton and WG gamma, these two backgrounds are estimated simultaneously. It means that the scale factor of these two backgrounds are calculated using the template fit on delta phi variable, because fake lepton will have some MET which is from the jet mismeasurement, whereas W or G plus gamma has a true MET from neutrino. So the delta phi between lepton and MET will have different shape for jet faking as lepton and W or G gamma. So we take these two template and get the scale factor for these two backgrounds simultaneously. And for electron faking photon, we calculate we estimate the background using G2E tag and probe method. And for jet faking as photon, we calculate first hadron fraction and then fake rate and apply it to the proxy sample to get the estimate. But I will be discussing this background in detail. So here comes the fake electron faking as photon. So we can have a fake photon that comes from that is actually a electron when electron doesn't have a signature in the tracker detector, and that usually come from Drellian events or TT bar or WW events with EE and EMU in the final state. We can have a electron faking as photon, and in the final state it will appear as photon and lepton. So to estimate this background, we use a very simple method, that is the fake rate of this process times some proxy sample. We define proxy sample as lepton photon events where electron is faked as a photon. So when electron is faked as a photon, photon have a pixel seed and it matched to an electron within a delta of 0.02. So this is the way we require that photon is a fake photon. And to calculate the fake rate, we use the tag and probe method. And the fake rate is number of E gamma divided by number of EE. So the ratio tells that when we have a electron faking as photon, this is the ratio. So we multiply the fake rate on proxy sample, and further we check the dependence of fake rate on PT of the probe and number of vertex, that is the pile of, and eta of the probe. So we parameterize the fake rate in this function and have the number A, B, D and E, and we use this function as an event weight to the proxy sample to get the estimate of this background. So here is the plot for fake rate dependence on PT of the photon and number of vertex. For eta we take the bin wise value directly, because this looks some trend and we can fit some function and get the parameter A and B, but for eta it is not showing any trend, so it is difficult to fit and we take it as a bin wise. So we get the fake rate dependence on PT, eta and number of vertex, and finally we can have the estimate of electron faking as photon background. So before moving to other background estimation, I would like to discuss some of the variables. Those are charge hadron isolation variable. It means that the sum of all PT of all charge hadron within a cone of delta R 0.3 surrounding the photon. And the other variable is Sauer shape variable, which show how the Sauer shape is distributed laterally in the electromagnetic calorimeter along the eta direction. These two variables are very important in terms of distinguishing the prompt photon and hadronic photons, because prompt photon will have a narrower Sauer and non-prompt photon will have a broader Sauer shape, and the charge hadron isolation tail will be longer for the non-prompt photon, where we have a pions decaying to 2 photon. So these two variables will discuss further, and the other variable is mini isolation, that is the ratio between the PT of lepton divided by PT of the cone, where the PT of the cone is the sum of the all charge particles surrounding the lepton including the lepton PT. So and the cone size is variable. This is important to note, because this mini isolation variable works very well in cases where we have a lepton within a jet, like top decays to BW and we have a muon from W decay, and to isolate those muon, this variable is very useful. The other variable is the angular distance between lepton, PT and mat. As I discussed previously, that for W gamma we have a true mat from neutrino, but for jet faking as lepton we have a mat from the jet mismeasurement. So this delta phi variable is useful in terms of distinguishing these two kind of background, that is the W gamma and fake lepton background. So moving to the next background estimation, that is jet faking as photon. This kind of events happen when jet energy is mostly carried out by pions or eta, and pions decays to 2 photon. This background is estimated the same way as the previous one. We estimate the fake rate and multiply the fake rate to the proxy sample as an event weight. The same way we defined as the electron faking photon, we define the proxy sample as L gamma events, where photon doesn't pass the selection of Sauer shape cut and charge hadron isolation cut. It means the photon have a longer charge hadron isolation tail and broader Sauer. That is the case when we have a jet faking as photon. And we calculate the fake rate by first estimating the hadron fraction, which is shown here. Hadron fraction is the contribution of hadronic photon in the data. So here is the template fit. The black point shows the data, and the green distribution shows the contribution from the hadrons, like pions decays to 2 photon, and the blue one shows the really prompt photon. So from this we look the signal region, that is 0 to 1.694, that is the hadron. When we have a small charge hadron isolation selection, that is the signal region. So in the signal region we look for the hadronic contribution. So integral of green divided by the black integral gives the hadron fraction. This is for one of the PT beams. Similarly, we calculate the hadron fraction for all PT beams, and we multiply the hadron fraction to the total number of signal photons. Because we have already estimated the electron fake photon, so we subtract that and we take the total number of proxy sample. So the cases where we have a jet faking as photon, we take the total number of events, total number of proxy sample in the denominator, and that gives the fake rate. So here is the fake rate, that is the ratio of number of fake and number of proxy, and we use this fake rate, we parameterize this fake rate as some analytic function and get the number C1, C2 and C1 to C4 and lambda to lambda 4 from this fit. And we use this fake rate as an weight to the proxy sample to get the jet faking as photon estimate. So moving further, these are the V gamma and rare backgrounds. These are taken directly from simulation. The point to note here that for V gamma background, we get the scale factor from the template fit. So here comes the jet faking as lepton. So when we have a lepton that is not originating from W or G decay, we consider it as fake for our analysis. So fake muon mostly comes from heavy flavor quarks, and fake electrons comes from light flavor jets. So the same way as previously, we define some proxy sample where we have a jet faking as lepton, and we get the scale factor from the template fit. So the lepton proxy sample is defined as one candidate photon that passes all signal region selection and one fake lepton which does not pass the mini isolation selection. So it has more mini isolation. It means that there is more hadronic activities surrounding the lepton. So it is some jet faking as lepton event. So we inverted the mini isolation cut, but keep all other selections same as before, same as for the signal lepton, and we calculate the scale factor to get the delta phi fit, which I will talk in the next page. So here comes the fake lepton and true lepton. So we have a true lepton from W gamma and fake lepton from jet faking as lepton. Since we already discussed electron fake photon, jet fake photon, and this background is taken directly from simulation, so these two are data driven and this is directly simulation. So we have remaining number of events, that is in the data, and number of lepton photon events in the data subtracted by all this what we have already discussed. So we use this event as a fitting target. This is the black points, and we get the two template for fake lepton and for true lepton. Those are shown as red and green distribution. You see that the shape of delta phi is actually different for fake lepton and true lepton, and from this fit we can get the scale factor for these two background. Once we get the scale factor, we multiply the scale factor with this two template and get the corresponding contribution of W or G gamma events and fake lepton events. So these two plots are, one is for E gamma channel and the other is for mu gamma channel. So moving further, as we discussed all backgrounds estimation method, so here comes the data versus standard model background in the control region. So the control region is defined by MAT less than 70 GeV, where we expect quite a large number of background events, and in all this plot the data is shown by black points with error bar, and standard model background prediction are shown as color histogram. The upper plots are for E gamma channel and the lower plots are for mu gamma channel. Here is ST, MT and photon PT and lepton PT. You see that data doesn't agree quite well with the standard model background prediction, and this is something we are trying to understand, if we can assign some uncertainty, then we can move further in the analysis, but it is clearly visible that there is some trend in the high MET and high ST region. So we are trying to understand this right now, and then we can move further in the analysis. So here comes the summary. So we are ongoing with this analysis, and we are trying to have a better agreement in the control region plot, or otherwise trying to understand why that trend is coming if we are missing some scaling. And we are planning to update the status in our internal CMS meeting. That is the full status report. That is maybe the first step for going for the analysis to be progress within the collaboration. And we are also working on the comments by the conveners, and in the next phase we'll either once we are done with the control region checking, we will look at the signal region, and we either expect that maybe SUSY signature is found, or we may get a null result, which will push the SUSY limit further, bypassing the previous limit set with only 16 analysis. So that's all. Thank you.
So thank you, Tribeni, for the talk. So maybe if we can have one or two quick questions.
Yes. So this is the limit, last limit. So for the T5WZ, this is on gluino and neutralino, and similarly for here quark and neutralino, and here is on this chargino neutralino, yeah, NLSP, yes. This is the last limit with 16.
Last part is the interesting one. Actually, can you show me the okay, I cannot see it properly. What is the expected limit?
You mean for with RON2 data?
Yeah.
RON2 data I made for T5WZ, but not with the, TKWZ one.
Without the, okay, charginos you have not. Okay.
We didn't have the sample, so I tried with T5WZ to get the expected limit for full RON 2, and we see some improvement of 140 GeV. This is the expected with RON 2, and this is the previous limit, and I find some improvement.
Thank you. So the analysis itself is 1 point something.
You mean here it is 1.7, this is Gluino,
No,
but
not blue. NLSP.
okay, here it is 930. This is the last year.
Thank you.
Sorry, I didn't understand what was the empty there. Empty in the constraint slide.
Which slide?
In the I think second one.
Okay.
Yes.
This is the transverse mass. If you look the decay of like W to L nu, and nu is the mat, and like W to L nu, if you try to get the transverse mass of lepton and mat, lepton and neutrino. So this is the general calculation that you can do. The delta phi is the angle between the lepton and neutrino.
So here we take delta greater than 0.8, right? But I think in the sampling you took 0.2, less than 0.2, right?
Okay, so this is like we want something isolated so that it is not a something fake object. So we want a well separation, but 0.02 this is where you mean here. So here we want to check that photon is a fake. So photon match to electron at a very small close distance. So if we have very small cut, then it is really matching with the electron track. The photon is really matching with the photon is very less separated to the electron. So this is the way we define the proxy sample when we have a electron faking as photon. So we want photon and electron to be very close, so that that sample will means that we have a fake photon from electron. Like, is it clear?
So maybe we can thank Tribeni again and all of the speakers of this session. So